This is the introduction to evolution. So we're going to be talking about a lot of different aspects of evolution, and you've probably heard of evolution. I hope so. You may have learned about it previously. I want to go through and make sure that we understand a few of the basics before we get into some of the more complex bits about evolution. So let's start. We're going to start with defining evolution. In common language, sometimes people say they have evolved or society has evolved. But when we're talking about biology, we are talking about a change in a species over multiple generations. So one species, let's say mosquitoes, over multiple generations changes and becomes less aggressive about biting people and more aggressive about biting pigeons. That would be a small example of evolution. The speed of evolution, how fast a species changes. I say over generations. This means it's not in one individual. It's from one group of individuals, all of the same age. They have offspring. Their offspring have offspring. Their offspring have offspring. Each one of those is a generation. And so the rate of evolution depends on how fast that species reproduces. So bacteria, which can reproduce in as little as half an hour, it doesn't take very long for them to change and evolve. There's a great experiment that demonstrates the evolution of antibiotic resistance to very, very high levels of this antibiotic in about 10 days. So in 10 days, they went from a species that could not survive the presence of this antibiotic to one who had no problem with it. Short-lived species like mosquitoes, those can evolve in a few years. The longer a species lives, the longer it's going to take for evolution to happen. We're dealing with climate change. We're going to talk about that in a later lecture. But short-lived species are starting to show changes as a result of climate change. They're showing evolution to adapt to the changing climate. Longer-lived species are going to have a much, much harder time dealing with the unusually rapid change in the environment. And of course, the size of the change affects the time. You can go from one fish to a new species of fish in maybe a few decades. But if you're going from a fish to a salamander, that's going to take something like millions of years. The last thing I've got on this slide is that traits can be lost as well as gained. When we think about evolution, when we learn about evolution, we generally talk about new traits that come about. But you can lose things. 20 million years ago, 30 million years ago, our ancestors had tails. Somewhere between then and when we split off from gorillas, we lost our tails. So you can lose traits as well as gain them. Okay, so that's time. But the other part of the definition is within a species. So we have to define a species. Well, biologists are still arguing about this one. This is kind of the best definition we have right now. But biology does not read the textbook, and a lot of organisms don't fit this definition very well. So we say that a species has common physical traits. They look similar to each other. A species has common strategies for living. This means they all eat the same thing. They live in the same type of habitat. They have a common way of interacting with each other, including things like finding and attracting mates, as well as are they territorial, are they social, these different strategies for survival. And they can breed and produce fertile offspring. So they can breed to each other and their offspring can have offspring. So there are some organisms like the mule, which is produced by a cross between a horse and a donkey, and those mules are sterile. They can't have their own offspring. So we wouldn't call that a species. Okay. And I do want to give you some examples of why the concept of species is not that easy to define. I'm going to give you two great examples here. On the left, we have a deep sea anglerfish. This is the triple wart sea devil. And I chose the drawing rather than a photograph because the drawing shows very clearly both the female and the male. In this fish, the male and female do not look very similar at all. Look at the size difference there. They do not eat the same things. The female is a predator. The male is a parasite. So the male, when it finds a female, attaches to her, and basically she provides all of the nutrition the male needs. And he stays attached to her and produces sperm for her, and that's all the male does. The female lives like a typical fish. She swims, she hunts, she avoids predators, all of that kind of stuff. So if you looked at just a female and an unattached male, a male that hadn't attached to a female yet, even if you studied their feeding habits and whatnot, you would never put these two things together and call it a species. But they are clearly the same species. On the right, we talk about plants. Oh boy, when we talk about species, plants, yeah, they do things very, very different from animals in certain respects. And in some situations, both animals and plants can crossbreed or hybridize, like the donkey and the horse, but produce fertile offspring. And it's pretty common in plants. Very common in, for example, oak trees. These are columbine flowers. And in this image, there are two different species and two hybrids between those two species. But they're all fertile. They can all breed together. Physically, they're different. Genetically, they're different. And where do we draw the line between the species? It's really, really hard in plants because they can hybridize so readily. This is one way humans create new food crops or new plants for the garden. A prime example of human-influenced hybridization is the citrus fruit complex. There were 3 original species of citrus: the true mandarins, the pomelos, and the citrons. Now, we don't usually see pomelos and citrons unless you're into non-typical foods. But when we think about citrus, we think about oranges, grapefruits, lemons, limes. Those have all descended from these 3 original species because of both natural and artificial hybridization. So we have selected to create oranges, lemons, limes, grapefruit, and there are actually now hundreds of different citrus fruits. And if you think plants are crazy, don't even try and figure out species with bacteria, because they really don't adhere to any of these rules that we have to try and create this definition of species. So the idea of a species is what I like to call an artificial construct. It is humans trying to organize nature into nice, neat little compartments. And sometimes it works and sometimes it doesn't, because in biology, things are not separated into nice, neat little compartments. What we can say about species is individuals within a species are related by a common ancestry, and closely related species are related to each other by a common ancestry. We can also say that 99%, over 99% of all species that have ever existed are now extinct. Some of these changed into something new. They evolved into a new species, and some were just outcompeted and died off. Extinction is a normal part of evolution. Evolution occurs because nature is not stable. The environment changes. Historically, the environment has changed relatively slowly over relatively long periods of time. Nowadays, in the past 200 years or so, we have really changed the environment, and species have to evolve to adapt. Change is the only constant in biology. Okay, so there are a lot of misconceptions about evolution. A lot of things that people believe that really are not true. So first off, evolution is not moving in a specific direction. If we wound back the time and started evolution on this planet again, we probably would not end up with the same types of organisms we have now. We might have plants and animals, but there's nothing that would guarantee that humans would arise again, for example. Evolution does not create new traits or characteristics. What do I mean by this? No matter how valuable a trait might be for a species, evolution does not create it. New traits come about because of genetic mutations, and those mutations are random. Evolution selects which of those mutations are going to end up becoming more common in the species. This will become clear in a future lecture when we talk about the process a little bit more. Evolution is not moving towards perfection. We're not creating a perfect organism over time. And I want to give you an example. This example is also a good example of cost benefit. So some evolutionary changes come with a cost. Childbirth in humans is a very, very dangerous process, and it has very high mortality without modern medicine. There used to be about 1 maternal death, the mother died, per 100 to 200 births. So that means about 0.5 to 1% of all women would die because they got pregnant. Wow. That doesn't sound like something evolution would select for, right? But evolution is selecting for big brains in humans. Our big brains make us very, very successful as a species. But they also make it much, much harder for women to give birth. With modern medicine, childbirth mortalities is about 1 death of the mother for every 30,000 births worldwide. In the US, we're at 1 death per 23,000 births. Wow. That's kind of embarrassing, isn't it? Okay, so to sum this up, evolution is a non-random selection of random variation. So there's variation within a species that's random, that occurs because of genetic mutations. And evolution selects those characteristics that produce the highest rate of survival.